Now we will look at lab 6, RLC resonance, bandwidth and quality factor. So basically we will consider this simple series RLC circuit. So the idea is if the frequency of the source increases, the capacitance will decrease in its reactance, and the inductor will increase in its reactance. So there should be such a frequency where they become equal, and at that frequency the circuit is purely a resistive circuit, acts like a purely resistive circuit. So if frequency is increased and this is the reactance, the capacitance should change its reactance like this, whereas the inductor will change its reactance like this. So this is the frequency where the reactance of the capacitor and the reactance of the inductor become equal, but in effect they eliminate the effect of each other. So the circuit will have maximum output at this, as it will act as a purely resistive circuit. So the frequency, this is the phenomena of resonance. The frequency at which it occurs is called the resonant frequency, and resonance is the condition where the reactance of the capacitor and the inductor becomes equal. So we will look at this circuit, which is our experimental circuit, a simple series RLC circuit where we have a 0.1 microfarad capacitor, a 560 microhenry inductor, and a 100 ohm resistor, and the source is 3 volt peak and 1 kilohertz. So we will construct this circuit, and this is our data table. So we have two sets of tables, one for a circuit where the resistance value is 100 and another where the resistance value is 200. We'll just focus on 100 ohm resistance in this video. So first of all, what we are going to do is we are going to measure the values. So the nominal value of R1 is 100 ohms, capacitance is 0.1 microfarad, and inductor is 560 microhenry. And if we measure the practical value, we are measuring the practical value of resistance using PMM, taking it to the resistance measurement mode. We see that the value is 96.4 ohm. We will record this in our table. As for the capacitor and inductor, we will use the LCR meter. First, let's record the value of the capacitor. So I set it to 2 microfarad setting. So 0.105 microfarad is the practical value. For the inductance, we will take the LCR meter to 2 millihenry settings. So the practical value is it's 559. So the practical value is 559 microhenry. So 559 microhenry. So we have recorded the practical values of the equipments, of the components that we will use in this circuit. So let's construct the circuit. It's a simple RLC circuit which we will construct in this manner. So first I place the capacitor, and place the inductor in series to the capacitor, and then place the resistance in series to the inductor. So we have placed the capacitor, the inductor, and the resistance in series. So according to our circuit diagram, we see that the junction between the capacitor and the node between the capacitor and inductor is node B, and the inductor and the resistor is node C. So this would be our node B, and this is our node C. Now we attach our function generator, which will be our source. So from the circuit diagram, we see that the source is connected between node A and node 0. So I attach the red wire to node A and the black wire to node 0. So we have completed our circuit. Now we will attach the oscilloscope. I will attach this black wire of the probe to the ground as always, and this positive end of the probe to node A. This is channel 1. I have placed it in node A so that I can calibrate the input to this 3 volt peak and 1 kilohertz setup. For channel 2, I will connect it in node C. As always, the black wire goes to the ground and the red wire, the positive end, goes to node C. So now we can start taking the readings from our oscilloscope and record the readings accordingly here. So for this experiment, what we are going to do is we are going to keep changing the frequency. Start at 1 kilohertz, and with 10 kilohertz increment we go to up to 100 kilohertz, and for each of these frequency we record the voltage across the resistance, voltage across the capacitance, and voltage across the inductance. So ideally what we will do is we will set frequency to 1 kilohertz and take all these 3 readings, set the frequency to 10 kilohertz and take all these readings. However, since we have a 2-channel oscilloscope, continuously changing the position of the probe to get these 3 readings is quite cumbersome. So what we will do is we will attach the oscilloscope to take VR first, and then we will increase the frequency and take the readings for VR for all of this frequency. Then we will go back to frequency of 1 kilohertz and repeat the same process and take the readings of the voltage across the capacitor for all of these frequencies, and the same goes for the inductor. Okay, so we turn on the function generator by pressing the power button, and we turn on the oscilloscope by pressing the power button located on top. So we see that by default the input frequency is 1 kilohertz. However, the signal is as triangular, and we change it to sinusoid by pressing this button. So what we need to do is we have to change the amplitude of the source to 3 volt max. So we see by previous settings that channel 1 Vmax is already being displayed here as 2.48 volt. So I'll increase it to 3 volt. So here we have 3.04 volt and frequency is 1 kilohertz. So from channel to Vmax we will take the reading for the VR, the voltage drop across the resistance, because it is connected in node C. So since channel 2 is connected in node C, we are currently getting the peak voltage drop across this resistance in our channel 2. For 1 kilohertz, we see that the output is 200, and So we see that for 1 kHz the output is 216 millivolts. Then we increase the frequency to 10 kHz. However, we see that at the max position of the frequency knob, the output is 6 kHz. So we need to change the range. I reduce the knob down and press the 10K button to increase the range. So now the output is 12 kHz. So I reduce it to 10. Okay. So we have 10 kHz. Now we adjust our oscilloscope horizontal and vertical settings appropriately. So you see that the amplitude has dropped to 2.3, so we will increase it to 3. The input needs to be 3 volt. Okay, so at 3 volt input, 10 kHz, our output is 2.08 volt. Next we move on to our next reading, which is at 20 kHz. So at 20 kHz our output is 2.48. However, we said that the amplitude has dropped again, so we should readjust it to 3 volt. This is the input, don't confuse it with the output. The input should be increased to 3 volt because our input is 3 volt max for every frequency that we are setting. So now we see that our output is 2.80 volt, and we record that value in this table. Next we move on to 30 Hz. At 30 Hz we readjust again. We see that our output is 2.64 volt. For 40 volt, so for 40 kHz, we see that our output is 2.24 volt. For the next reading, we set the frequency to 50 kHz. At 50 kHz, our output is 1.92 volt. Next, 60 kHz. At 60 kHz, our output is 1.76 volt. Then our next reading is for frequency of 70 kHz. However, I have reached the maximum position of the frequency knob, so I need to change the range to 100K. So I reduce the knob down and then press 100K. Now I set our 70 kHz. I readjust the amplitude to 3 volt. So our voltage drop across the resistance now is 1.56 volt, which is recorded. Next, we change the value to 80 kHz. For 80 kHz, our output is 1.30. For 90 kHz, our output is now 1.20 volt. The last frequency setting is 100 kilohertz. At this frequency, our output is now 1.08 volt. As you see, as frequency is increased, the voltage drop across the resistance increases first, reaches a maximum value of 2.8 and then drops again. Okay. So now we will repeat the same process for our capacitance. To get the value of our capacitance, to get the value of the voltage drop of the capacitance, we need to move channel 2 from node C to node D. Then channel 1 is already connected to node A, so VA minus VB, which is channel 1 minus channel 2, would give me the voltage drop across the capacitance. So I move the channel 2 from node C to node D. So now we see that our frequency is already set to 100 kilohertz, that which was the last reading for our resistance. What we'll do is we'll take this reading for the capacitance, since already the value is set. So I'll reduce the output here. Channel 1 minus channel 2, so we need to perform math. Channel 1 minus channel 2, this is the curve of the capacitance voltage. So we'll measure this value using cursor. Source would be math, type should be voltage. Now we'll move cursor B to 0 volt position, and move cursor A to the peak of the new curve, the math curve. So the voltage drop now here is 120 millivolt. We record that value of 120 millivolt here. Next we decrease our source value to 90. We press measure and see that our amplitude is okay, so we take the reading. So the peak value is now 160 millivolt for 90 kilohertz. For 80 kilohertz, we have 200 millivolt. For 70 kilohertz, we have 240 millivolt. For 60 kilohertz, our output is 320 millivolt. For 50 kilohertz, our drop across the capacitor is now 440. Going to the next reading, which is 40 kilohertz. Our capacitor voltage has now increased to 640 millivolts. Going to the next value, let's check at the amplitude. It should be increased to 3. So going back to the cursor, we find that at 30 kilohertz our voltage drop is 1.2. Going down to 20 kilohertz, the voltage drop across the capacitor is 1.84. For 10 kilohertz, we need to readjust. Okay. So since channel A is still connected to channel 1 is still connected to node A, this channel 1 Vmax is the input voltage, so we recalibrate it. For 10 kilohertz, our output is 2.64. Cursor B should be 0. Okay. So 2.68. And finally, for 1 kilohertz, I need to reduce the range. So for 1 kilohertz, recalibrate the amplitude and go back to cursor. Cursor A is 2.96 volt. Okay, so we'll now repeat the same process for the inductor. So we'll now repeat the same process for the inductor. For the inductor, if we refer to our circuit diagram, the inductor is placed between node B and node C, so we need voltage of B and voltage of node C. So VB minus VC will give us the inductor voltage, so we have to move channel 1 to node B and channel 2 to node C, or we can since channel 2 is already placed in node B, we just move channel 1 from node A to node C. So I'll do that. I'll move channel 1 from node A to node C. Well, I was recalculating the value for the resistance. So my channel 2 is placed in node C. So I'll just move channel 1 to node B. So minimum amount of effort. So now channel 1 minus channel 2 will give me the voltage drop across the inductor. We recalibrate the screen. State position required. So after a bit of stabilization, now we have this output. We see that math is channel 1 minus channel 2. So this purple waveform is the output of the inductor, and we will measure the peak voltage of this curve. This is the output of the this is the peak voltage of the inductor. So going back to cursor, we move cursor A to the peak of this curve, and we find the value of 66 millivolts. So at 1 kilohertz it's 66 millivolts. Increasing to 10 kilohertz, we need to recalibrate the waveforms in our screen so that it fits the screen. If you press the math button, we find that it's been recalibrated. So going back to cursor B is at 0. We move down cursor A to the peak and find the value of 200 millivolt for 10 kilohertz. Setting to 20 kilohertz and going back to the cursor, we find that the output is 920 millivolts. For our next reading of 30 kilohertz, we readjust and the value is 1.72 volt. Then for 40 kilohertz, our output is 2. For 40 kilohertz, our output is 2.64. Setting the frequency to 50 kilohertz, the output is 2.80. At 60 kilohertz, our output is 3.08 volts. we cannot go any further, so we change the range and set to our desired 70 kilohertz, and we find that the output is 3.28. For 80 kilohertz, our reading is 3.36. For 90 kilohertz, our output is 3.44. And the last piece of reading at 100 kilohertz is 3.48. So as we see, as frequency increases, we know that the reactance of capacitor will decrease, and that is reflected by the fact that the voltage drop across the capacitor is decreasing with increasing voltage, and and when the frequency is increased, the reactance of an inductor will increase, and that is reflected by the fact that the voltage drop across the inductor increases as frequency increases. We see that the output across the resistance changes from 216 millivolt to 2.08 volt to 2.8 volt, and then drops down to 2.64 volt. So we reach a maximum voltage in the region of 20 kilohertz to 30 kilohertz. So we can say that the resonance frequency, where the reactance of the capacitor and inductor becomes equal, is in the region of 20 kilohertz and 30 kilohertz. So if we analyze this range, we will be able to find our resonant frequency, F1, F2, and from there we can calculate the bandwidth. Now that we have recorded all the voltage drops across the resistance, capacitance, and the inductance for all the frequency range, now we have to determine the cutoff frequency, F1 and F2. We will do that by looking at the peak drop across the resistance and find the maximum value. Since at 20 kilohertz the maximum value of 2.80 volt is reached, and at 30 kilohertz the value is dropped to 2.64 volt, we can investigate this region from 20 kilohertz to 30 kilohertz to find the maximum value. So we'll set the frequency at 20 kilohertz and then gradually increase up to 30 kilohertz to find the maximum voltage drop, and see if there is a higher voltage drop across the resistance at greater than 2.80 volt. At a resonance condition, the capacitor and inductor will have equal inductance, have equal reactances, and the circuit will behave as a completely resistive circuit. So the maximum voltage drop will be observed at the resistance. So we will take the output of the resistance to determine the cutoff frequency. So previously our oscilloscope was attached for measuring the voltage across the inductor. So channel 2 was connected at this node and channel 1 was connected at this node. We will shift this node, shift this channel 1 to the input side, so that we can maintain the amplitude of 3.0 peak volt. So now if I press measure, I see that let me turn off math function. and I change the frequency to 20 kilohertz. The range is reached, so okay, so let me add this channel 2. So now we have a signal at channel 2. Okay, channel 1 Vmax is 2.56, so I'll increase the amplitude to 3. Okay, so I have adjusted the input to 3 volt, and now you see that at 20 kilohertz we have a voltage max of peak voltage of 280 volt at channel 2, which is the drop across the resistor. We will keep increasing the frequency and observe if we get a higher voltage drop. So we can say that the cutoff frequency is around 20 to 21 kilohertz. So we'll record that in the table because we don't get any output voltage higher than 2.80 volt. So we will record this value as the cutoff frequency. So our practical cutoff frequency is around 21 kilohertz. Now we have to determine F1 and F2. So F1 and F2 frequencies where we will reach 70.7% of the maximum voltage. Our maximum voltage is 2.80 volt. So we will get one lower frequency where we will get a value of 70.7% of 2.8, and at a frequency after the cutoff I will get the same voltage. So let's determine the voltage where we should look for these frequencies. So 2.80 volt into 0.707, 70.7%. So that is 1.98. So 0.707 Vmax is 1.98 volts. So we'll look for frequencies where we get output voltage of 1.98 volts. So to determine F1 and F2, we will change the frequency. One will be below the cutoff frequency, that is below 21 kilohertz, and one will be higher than cutoff frequency, that is higher than 21 kilohertz. So we will adjust the frequency until we get a value of 1.98 volt. So I gradually decrease the frequency. I adjust the amplitude of the input to keep it at 3 volt peak. Okay, so at 10 kilohertz we get 1.92 volt, and at 11 kilohertz we get 2 volts. So 2 volt is closer to 1.98, so we will record the F1 as 11 kilohertz. We record 11 kilohertz because we get 2 volts of output at this frequency, which is very close to our required 1.98. So we have determined F1. Now we will determine F2. So we'll have to go to a frequency higher than the cutoff, that is higher than 2.21 kilohertz. So I'll keep increasing the frequency until I get a value of 1.98 volt or close to that. I repeatedly keep adjusting the amplitude of the input and keep it at 3 volt peak. I adjust the volts per division a bit. So 43.9 kilohertz. Since we took F1 at 2 volt, we will stick to 2 volt for F2, which is very close to our required 1.98 volt. So it's 43.9 kilohertz. Our bandwidth is therefore 43.9 minus 11, f2 minus f1, and it's 32.9 kilohertz. And our Q factor is 2.27 f0 divided by bandwidth 29. It's 0.73, and the practical Q factor that we got from our practical data would be 21 divided by 32.9, 0.64. Okay, so these are the practical values that we have got for our experiment on resonance. So this circuit has a quality factor of 0.64 practically and 0.73. The cutoff frequency is very close, 21 kilohertz. The F1 is also they're equal. F1 is equal 11 kilohertz for both practical and theoretical calculations. However, F2 deviated a bit from 40 kilohertz practically, 43.9 kilohertz experimentally.